Okay, the last speaker of today is Carlos Oliveira, who is second last speaker of today. Who told me that? The second last speaker of today is Carlos Oliveira, who is a member of the University of Lisbon, a law school. Like everybody else, he has been contaminated by Schrödinger problem in recent years, with a very simple question. The original problem of Schrödinger, you give me a time interval, 2 probability density, what is the interpolation? Same question without having a deterministic time interval. So you want to define a critical point in space-time. Believe me, in physics, this is not irrelevant. It will be nice to have something like this. So he's going to describe this kind of result.
So, thank you very much for the introduction. As you could saw, so Jean-Claude could present my work perhaps better than me. So let me just say thank you for the invitation. So thank you, the organizers, for preparing this meeting, because I guess that it's not easy to organize a meeting under this COVID situation. So this is the title of my presentation is Time-symmetric optimal stochastic control problems in space-time domains. So this is a joint work with Annabella and Jean-Claude. Just for my defense, let me tell you that my background is in economics and management. So I do applications, not in physics. So I did my postdoc with Jean-Claude and Annabella. So, well, I will try my best to explain you our results, but sometimes it's hard for me to understand your applications to physics and so on. Okay, so the main idea of this work is to understand how can we construct these Bernstein processes in space-time domains. So in a random domain, let's say. Okay, so the outline of my presentation is here. So firstly, I start with the motivation, where I will present the main results about Bernstein processes, so the main definitions. I will also show you some concepts about hidden diffusions. Afterwards, we will move on to the stochastic control problems, where I will show you the AGB equation, so some existence and uniqueness results. We will move to the characterizations of the optimal times that we get in these stochastic control problems, and afterwards I will very briefly explain 2 extensions where we are working on. Okay, so let me just see if I have the time just to, no, okay. So we start with a process Z that is defined on a filtered probability space with 2 sigma algebras. So 2 filtrations, one that is increasing and another one that is decreasing. We know that Z is a Bernstein process when these properties is satisfied. So basically the expected value of f of zt conditional to the 2 filtrations is equal to the expected value of f of zt conditional to the initial information, let's say, in the last information. So this is weaker than the Markov property. So we have Bernstein processes that are not Markov processes. And as you know, this process can be called reciprocal processes. So there are a lot of research where they do not call the processes Bernstein processes. Okay, so the idea to construct the density of these processes, as you already mentioned during this day, can be to multiply 2 positive functions, one that is a positive solution to this initial value problem, and another one that is a solution to this final value problem. So we have two equations that are adjoint. Our operator H is defined in this way, and H bar is a positive constant. Okay, so when we have Z a Markov diffusion, we know that Z satisfies simultaneously this forward ST and the backward one. The drift can be defined in this way. So it's basically the h bar grad log of eta, so the one of the positive solutions of that terminal value problem, and the backward drift can be defined similarly. So there is this explicit relationship between the two drifts, so the backward drift and the forward drift. We can define the forward and backward infinitesimal generators for this process. So this is everything very well known. Okay, so when we are in this quantum-like context, we know that these processes can be obtained as critical points, let's say, for these forward and backward action functionals. Of course, in the classical theory, we do not have here this random time tau, so the integrals are between t and t over 2, or between minus t over 2 and t. So S in here is the terminal condition, and S star is the initial condition, V is the potential function. So when we move to the stochastic control theory, so we know that these Bernstein diffusions can be obtained as solutions of these two control problems. So basically, we are controlling the drift, and we know that we can find this function f and f star as classical solutions, at least when V is regular enough, and also the terminal conditions, as classical solutions to these two HB equations. So if we use this change of variable here, it's quite easy to understand that there is a relationship between f and the solutions of these initial and terminal problems. So if we have eta and eta star, we can also compute f and f star, and the reverse is also true. Okay, so now, so far we have the Bernstein process is defined between minus t over 2 and t over 2. Outside of this interval, we don't know what is happening, because perhaps this function eta and eta star becomes negative, so this is no longer a density. So we have the process well defined in this interval of time. So when we was thinking about this work, we find out this paper of Choi and Nam, published in 2004, where they deal with these hidden diffusions. So, well, the idea of these authors is not to work with the processes, with Bernstein processes. What they want to do is to estimate the diffusions, because this is related with sign-out processing. So they have the diffusions, they cannot see the diffusions in a certain domain, and they want to estimate the diffusions in that domain. So basically, they start with a process C that also satisfies these two SDs. So the drifts are defined in the same way, and afterwards, they have this auxiliary process YT that is basically ZT in a certain, outside of a certain domain, and is hidden inside this domain. So their problem is how to estimate the process when the process is inside the domain. So what they can prove is that the expected value of f of zt multiplied by this indicator function, conditional to this sigma algebra. So this sigma algebra here is basically the sigma algebra generated by zt when zt is outside of the domain, is equal to the expected value of f of zt conditional to the entrance moment. Well, the entrance or leaving, it depends on our position, but let's say the entrance moment, the leaving moment from that domain, and also the position of the process in the boundary. So, well, when we look carefully to this property, that's not difficult to understand that somehow this is generalizing this property. So our point here is to understand how can we construct Bernstein processes, so with the same properties, but in an interval of time that is random somehow. Okay, so our idea is to use this stochastic control theory to construct these processes. How can we do this? So instead of optimizing just regarding to the drift, we can optimize regarding the drift and the random time tau. So when we look to the forward and backward functional action functionals, we have here tau that can be optimized and also the drift. So we can optimize these functionals regarding the drift and tau. Oops. Okay, so to solve these problems, we impose some assumptions. So we are assuming that V, S, and S star are Lipschitz continuous. V is all bounded, and S and S star are such that these two families of random variables are uniformly integrable. Well, with the first assumption, we can prove that U and U star are both Lipschitz continuous. With the second assumption, we guarantee that these optimization problems are well posed. And more than these, we can prove that these two families of random variables are also uniformly integrable. So this is important to prove afterwards the uniqueness result for the AGB equations. Okay, so to optimize the action functionals regarding these two, so the time and the drift, we need these two AGB equations. So they are slightly different from the ones that we have when we are just controlling the drift. So formally, we know that the drifts that minimize the action functionals can be obtained in this way. So if we use this information, we can simplify these AGB equations. So, and basically we have the maximum between these two terms that must be equal to 0. So the value functions will satisfy these two equations and also the boundary condition. So how can we prove existence and uniqueness? So in general, we need two ingredients. So the first one is a dynamic programming principle, which is not a problem because we are working in a Markov setup. So we can use this dynamic programming principle that is borrowed from Krylov. Of course, we may use a more general dynamic programming principle. So there are weak dynamic programming principles. For instance, here in 2Z, they establish a dynamic equation between U and the upper or lower envelope of U. Well, in this case, we know that the function is continuous. But if you don't know the regularity of the function, these kind of weak dynamic programming principles can be useful. And more than this, when you have the upper and the lower envelope, it's very suitable to use the viscosity solutions. So, but for us, this dynamic programming principle is more than sufficient. So you have here some references where we can find more general dynamic programming principles in case we don't know the regularity of the function U. And the second, the second ingredient that we need is viscosity solutions, because we know that the function U and U star are continuous, so uniformly Lipschitz continuous. But in fact, this is not sufficient to deal with classical solutions. So what we do is to use viscosity solutions. So to prove existence, the idea is to pick these guys, so to apply Ito formula to this function U or to a more smooth function, and afterwards, together with some convergence results, we can prove that the function U and U star, they are both viscosity solutions to the previous AGB equations and satisfy these two conditions. So we have existence, but before we move on, let me just tell you one thing. So although we have here these equations and we have the boundary conditions, in fact, what we have here is a free boundary problem. So free boundary problems appear naturally when we have optimal stopping. And this is because, well, when we have the maximum between these two terms, what we are imposing is that each one of these terms must be non-positive. Otherwise, the maximum is not equal to 0. So basically, we know that this guy must be less than or equal to 0, this guy must be less than or equal to 0. If this one is strictly negative, this one must be equal to 0. When this one is negative, then this one must be equal to 0. Okay, and the same for the backward case. So this means that what we are doing is solving these PDEs in a domain that is unknown a priori, because the domain depends on the solution of the PDE. So what we can also prove is that these value functions u and u star are also viscosity solutions to these free boundary problems. So we have now existence. So the next step is to prove uniqueness. Okay, and the result is more or less like this. So we have a value function u, and this value function u is the unit viscosity solution to the HGB equation that satisfies this boundary condition, and additionally satisfies also this property. So this family of random variables is uniform integrable. So the optimal strategy can be defined in this way. So hat tau is the first moment when the value function u evaluated in the process z reaches the terminal condition. So is larger than or equal to the terminal condition. And formally, the drift is equal to minus grad of u. So we have a similar result for u star. So u star is the unit viscosity solution to the HGB equation, satisfying this boundary condition and also this property. In this case, we have the supremo because we are looking to the decreasing filtration. So the first moment is written as the supremo. So the idea to prove this result is the following. So we know that there is a solution. So we pick one of these solutions and we consider a domain, a compact domain. So for that compact domain, we know that this function in that domain satisfies an equation like this one, but with a different boundary condition. So there is uniqueness of viscosity solutions in this domain because we are in a compact domain. We can establish a relationship between this function and another control problem, and using afterwards a convergence result, we can prove a uniqueness of results, uniqueness of solution, sorry. Okay, so we have now uniqueness of result of solution. So just to finish the bridge, let's now look to these equations. So basically, if we use the change of variable, we get these two equations. So we had the maximum, now we have the minimum. These are also free boundary problems. So if we look to these equations written in this way, so these equations are basically the first equations that we have seen, but now the equations have to be solved in a different domain, and this domain depends on the solution of the equation. Okay, so having this information, what we can prove is the following. We can prove that the process Z that we are constructing solves simultaneously these two FDEs. So the density can be computed in this way. So the product of these two positive functions, and this, I would say, this local Markov property, I don't know if that's the correct name, is also satisfied. So somehow this generalizes the idea of Bernstein process. Okay, so let me show you now an example, just to see the difference of the stochastic processes that we get if we use the classical control problem and this one with the optimal times. So we consider, let's say, let's fix n equal to 1, so v equal to 0. So the terminal condition is the absolute value of x, and the initial condition is log of 1 plus the absolute value of x. Basically, in the first step, we want to solve these problems controlling the drift. In the second case, so in that case, tau is equal to just t over 2, there is no tau. In the second case, we want to control both the drift and tau. So if we are just controlling the drift, Well, what we have to do is to use a change of variable. So we have the AGB equation, we use the change of variable. And when we do this, we obtain these two adjoint boundary problems. Well, using a good book of its equations, we can end up in these solutions. So having eta and eta star means that we also know the density of the process and the drift. So everything is done for this case. Well, if we want to optimize the problems regarding the drift and the time, the things are a bit more complicated, although we have chosen functions where we can obtain explicit solutions, of course. So the idea is, if we start with an initial condition, Tx that is equal to, let's say, T0, so T can vary between minus T/2 and T/2, but X is equal to 0, that's quite easy to see that the optimal strategy is to stop the process. Why is this? Because if we stop immediately the process, this guy here is 0, and this integral will be 0. So we cannot obtain any expected value for this situation that is smaller than 0. So this is the optimal strategy in that case, which means that, we know that this region here is contained, in the stopping region. So where we should stop the process. Of course, we have to see if the stopping region is larger than this region. How can we do this? So let me show you again this part here. So if we know that V is equal to S, if we know that V is smaller than S, then we know that this guy must be equal to 0. If when this guy is equal to 0, then this guy must be non-positive. So we can pick the function S, replace V by S, and if this term is positive, then we know that we cannot stop the process, otherwise the AGB equation is not satisfied. So let's do this. So let's solve that equation or that term replacing V by S. For our functions, what we can check is that this term is always 1/2, which means that the function V, when X is different from 0, cannot be equal to S, which means that the stopping region is exactly this region here. So we only stop the process when C reaches 0. So, well, when we do this, we no longer have a free boundary problem, because we end up in the boundary for this problem. So we found the boundary for this problem, and now we know that we have to solve the PDE in the entire domain, excluding X equal to 0. So when X is equal to 0, we know that the optimal value of the Daxian functional is 0, and when T is equal to T/2, we have the terminal condition that is absolute value of X. So, well, for this case, as I told you, we have chosen the functions in such a way that we can get explicit solutions. So for this case, we can use the change of variable, and looking to this boundary problem and picking a good book about its equations, we can get this expression here. So having eta, we can also compute the optimal drift, and of course, we can compute the optimal tau. So the optimal tau is the first moment when the process reaches 0. So basically, if we just look to the forward SDE, what we are doing is constructing two symmetric versions of the same process. Of course, we need also the eta star to have the density. Well, and the idea is exactly the same. So we have a function S star that in a way that the stopping region is also minus T/2 until T/2 times 0. for this case, we can also get eta star given by this expression. So the optimal B star is not nice. So of course we can make the computation. So if you look to the paper, we have there the expression for B star, but in this case I don't have here the expression. And the tau star, the optimal tau star, is basically the first moment when the process reaches in zero. Okay. Okay, so with this we at least we think that we have understood that we can construct these Bernstein processes that are slightly more general than the first version. So the second point is to understand how can we characterize these optimal times. And the idea is the following. Well, basically what we want to do is to find this survival function, or if you want a CDF. Of course, in here we have to impose some conditions, some regularity conditions. Perhaps these conditions are quite strong, but well, at least with these conditions, we know that the function Q and Q star, sorry, Q and Q star are continuous. So what we are imposing is that we have a strong solution to these SDEs, and grad U and grad U star are basically ellipses continuous. So if we have these conditions, we can see the following. So in this slide, I have an auxiliary lemma. So basically, we have the non-interesting cases in this lemma. So yeah, in these cases, so if you look, basically we have an initial condition that is in the stopping region, or cases like this. And for these cases, it's very easy to see that the probability is always equal to 1 or always equal to 0. So these cases are not interesting. But when we are outside of these domains, so when we are in the interesting cases, what we can see is the following. So for that cases, Q and Q star are both continuous in the respective domains. And additionally, these functions, Q and Q star, satisfy these boundary problems. For these cases, we can prove that the function Q and Q star are the unique continuous viscosity solutions that satisfy the two boundary problems. Well, and that's it. So, well, we have time enough. So let me just show you two extensions where we are working on. So the first one is to understand the role of these optimal times. So there is an implicit relationship between the two, because when you look to these boundary problems, we know that the drift, the forward drift and the backward drift of the SDEs are related. So we guess that there is a relationship between the density function of these tiles and also a relationship between these two times. So what we are doing is to try to understand what is the relevance of these times in the theory of Schrödinger. Secondly, we are also looking to these problems. So if you remember the beginning, so in here we are optimizing these two action functionals. So we have the expected value of the integral of blah blah. So what we want to understand is how can we optimize this process? So of course we will not get a value function. We will obtain a value process because we are optimizing a stochastic process. This optimization is a pairwise optimization. We know that we have to think carefully about the class of processes that we can use in order to obtain the minimum. and the idea is, so we have already some results, and the idea is, instead of having an AGB equation, we would have a stochastic AGB equation that is basically a backward SPDE. And somehow we can prove that this value process will be a solution to this backward SPDE. So that's the idea. Well, and that's it from my side. Thank you. Yeah, sure. Sure.
So any questions? We check here. Yeah. Please.
Okay. So thank you. What do you mean by space-time domain? You mean the space and the time are, you mean from the Schrödinger point of view, the starting time is fixed and the ending time is fixed, but the position is random, right? Yeah. So in your setting, your starting time and the ending time is also random.
Yes. So the idea is when
Sorry. Merci, Christian. Sure.
So the idea is, when we have these Bernstein processes, we have a fixed initial condition and a fixed terminal condition. So we know that the process is well defined in this interval of time. When you construct the process in this way, you don't know when the process, in space, where the process is defined a priori, which means that you don't know when the process reaches this boundary. So you don't know the interval in time in which the process is defined. In this way, this interval in time is random, if you want.
I see. You have an entry time.
Yeah, and an exit time. Yeah. From.
One more question from Christian.
Thank you. So thank you. Very, very stimulating results and talk also. So the solutions are Markov processes. Yes. So then I mean a priori, because they could be reciprocal, but you have the result that they are effectively Markov process. Of course, this is Jean-Claude can guess my question. Probably there is an entropy minimization problem. And what would be the reference measure? So we need, because we have to introduce these stopping times and so on. And it would be a nice result to just to have this generalized Schrödinger problem, because all the results that you have shown are very similar to the simple Schrödinger problem. So I guess there is something to do in this direction.
Jean-Claude? Yes, I will say that it is possible to do something like this. Yes. There are other reasons to be interested by these, as you may guess, is that in a reasonable physical theory, especially relativistic, the space and the time should somehow have the same status. In the problem of Schrödinger, the original one, this is out of question. Curiously, in the same paper of Schrödinger, since you like archaeology of science, he complained about the status of time in quantum theory. And so in this sense, it is a natural question to ask. Personally, I didn't know that you could have those two time and that you could optimize in space-time. So it will be nice to see if we can localize some example. The problem is very practical. It is rarissime to be able to solve one of those open boundary value problem. It's awful. And if we can get some example, even in one dimension, it will be very useful.
And I am very excited to tell you all that we have a question from the internet. So someone is asking, is there any specific reason you have a particular noise coefficient, for example, square root of h in the SDE satisfied by ZT?
No.
Elaborate.
No. Well, yeah. Let me just say something. Let me just move to. Well, my answer. Well, if you ask Jean-Claude, he has a reason because there is a physical reason. For me, this is just a parameter, to be honest. So we could fix it in one. Yeah, but it seems that there is a physical reason to have here this h bar.
Yeah, but it would also have a
Yeah, sure. Yeah, we could also have here a different function. Well, I mean, when you look to these hidden diffusions, for instance, they have the relations with a more general function. So they do not fix the function in a constant. So indeed, you can have here a more general diffusion coefficient.
And for the Hamiltonian written initially, this is the right constant.
Okay.
Right?
Yeah. For this guy.
Yes, just past.
Yeah, this guy.
Exactly. So there is no choice for the Hamiltonian.
Okay.
Okay. So let's thank Carlos again. Thank you. And so since we're early, I suggest we just move on to the next talk, which is going to be Anatole Galouet. So technical break just to change screens.